Hi, welcome back to Hijax. This is lecture 4 of Act 1, and this lecture is called High Automatic Vectorization. So you will remember VMAP from the overture, and VMAP is our JAX transformation we're going to be learning about more in depth today. And VMAP is hands down my favorite thing from JAX, actually. So this is the tool that, as I said in the overture, lets us not worry about managing batch dimensions when we're programming. We can basically write all of our array functions to handle a single example, the smallest scale that the function sort of needs to worry about. And then we can just transform the function into one that automatically handles vectors, arrays, multiple batch dimensions if we want of sets of those things. And I still find examples in my coding, in my research, where I realize I'm having trouble coding something, and then I realize, hey, actually what I'm dealing with is trying to repeat this computation over the same fundamental unit, and I'm trying to manage that dimension. I should just be using VMAP, and it saves me a big headache. And so I really love VMAP. And so that's what today is going to be all about. Or actually, I guess that we'll be doing some more as well. We'll be getting some more practice with various things in the sort of JAX programming, the JAX way of array programming. So we'll get some more examples with pi trees and with JAX random and all of that. And we're going to do that by implementing another example, another famous neural network from the history of deep learning. And this neural network is called LeNet, and it's a convolutional neural network developed by Yann LeCun. This is a neural network that was designed to classify handwritten digits from the MNIST dataset, which is also pretty famous, and there's a good chance that you've seen this and maybe even trained some PyTorch models on it before. We're going to implement this neural network, which will give us a good chance to develop our understanding of these JAX concepts of pi trees, and particularly automatic vectorization with jax.vmap. And so, basically let's wind back to a simpler time decades ago, before Yann LeCun had a third of a Turing Award, and before he had some of the worst takes on the future of ethics and the future of technology in the entire world. And let's implement the simplified version of LeNet and classify MNIST digits. So I'm in the Hijax repository here, and I just want to point out that there's this data folder that contains MNIST. It's a pretty small file in sort of compressed NumPy folder, but this is all 60,000 plus 10,000 test images from MNIST and their labels. And so we're going to be loading that into our code. But to find that code, let's go to lecture 04, and we'll see this SimpleNet script set up for us for our simplified LeNet. So we've got the sort of scaffolding that we're used to by this point of a couple of imports from the standard library plus Tyro and matthewplotlib. We're going to be using functools today for some decorators. When we're registering pi trees, we want to register them with custom arguments. We've got JAX typing and typing again. We've got NumPy here, I think, for just visualizing images. And then we've got JAX, NumPy, and JAX for all of our actual computation. INOPS we're going to be using to help us manipulate images during the forward pass of the convnet. It's just going to be a little bit easier to use INOPS for some of these operations. We've got a main that's set up to have these command line arguments using Tyro. And we're going to be doing 3 things today that we're going to implement here. We're going to implement loading the training data, initializing the model, and then, of course, the training loop itself. We've got an architecture tab where we're going to work up to defining this SimpleNet, which is going to have a bunch of components laid out in the LeNet paper that we're going to implement. And then we're going to implement those components, and we'll have like a kind of hierarchy of elements composed together to build a more complex neural network than we have in the past. So this will be a good example of sort of modular programming with JAX. We're going to also have to implement some metrics. So in particular, the loss function, which will be a batch version of cross entropy, and we'll implement it in a slightly different way this time using VMAP than last time where we implemented it batched by hand. And then we're going to implement also a batched version of accuracy, which we'll use, test accuracy, which we'll use to sort of track the generalization of our network. And then, as usual, we've got some matthewplotlib Visualization code, this is just to sort of show dynamically how the network is classifying a few test images to see if it's on the right track and see what kind of mistakes it's making. And then we'll be able to look at some metrics as well, some learning curves that we'll plot as scatter plots while it's training, so that we can get a sense of the loss going down and the accuracy going up. And then we're just calling into the main function with tyro. So this stuff you can follow along with if you look at the GitHub repository in the lecture 4 file. It's worth noting that I also have the virtual environment set up, and I'm in the lecture 4 directory over here so that I can run this code. And so, okay, the first thing we need to do is load the training data. So in order to load the training data, I'm going to use jnp.load and then give it the path to this up/data/mnist.npz. Make sure I get that right, npz. And I'm going to load that as a file, as data file. And this is going to give me access to sort of a dictionary of the arrays in here. Unfortunately, even though I'm using the jax numpy version of np load to load this data file, it's still going to give me back the results as arrays, as numpy arrays, but I can just easily convert them to jax arrays like so. So we're going to have xtrain, which is going to be jnp, jnp.array, which is the command we use. You can just give this a numpy array and it will just turn it into a jax array. You can give it a list, it will turn it into a jax array. So we're going to give it the numpy array that comes from data file xtrain. And then we want to do basically the same thing for a couple of other things. So we want to do this for xtest, and then that will be xtest. And then we want to do this also for the labels. So that's going to be ytrain and ytest, and then ytrain and ytrain there, and ytest, and ytest also here. And so this is going to give us 4 arrays that we're going to be using for our training and test data, including the labels. And so we can already go ahead and take a look at this data before we do any learning with it. Let me start by just printing out maybe the shape of these arrays. So we can have xtrain.shape, and maybe also the dtype. So xtrain.dtype. And then let me go ahead and do that for the other things as well. So we can have xtest and xtest, and then we can do ytrain and ytrain, and then this will be ytest here as well. And then if I print this out, it should give us an indication of what we have loaded. So we have loaded, it's all uint8s, the data type, but the xtrain is a 60,000 array by 28 by 28. So this is a 60,000 images, and each image is 28 by 28 pixels, and there's no color channel. There's no extra RGB channel here. These are just grayscale images, and they're uint8, which indicates that they're stored as numbers between 0 and 255, representing the intensity of each of those pixels. So that's fine. We have also the same format. Xtest is 10,000 more of these, and those are the held out test set that we can use for evaluating the accuracy of our model. And then we have also 60,000 and 10,000 labels respectively. So these uint8s are just going to be digits from 0 to 9 inclusive. And that is what, those are going to be like the digits that we have actually in the handwritten digits. And so I think we should be able to get a look at some of this data already. So we can use matthewplotlib, which has an image plot function that can just take something like xtrain0, which is going to be a 28 by 28 uint8 array, and it can show it to us on the terminal. So why don't I go ahead and do that? And I can see we have a beautiful handwritten 5 here. And we can just confirm that it is, in fact, classified as a 5 according to the creators of MNIST by also printing out ytrain0, which is going to print out 5 there. And so that is what we hope to see. And so, okay, so these, one more thing we have to do to prepare the data is some scaling. And so Yann LeCun's paper sort of points out that it's nice to have your neural networks work on data that is not so large as 0 through to 255, because that creates very large activations, which creates very large gradients, makes everything a little bit less stable. And it would be nice if we had these on a sort of standardized scale. And in fact, if you go and calculate the mean and the standard deviation, I don't know if that's exactly the calculation, but you can make this so that it's a balance. And the balance that he found and put in the paper was that we should take xtrain and we should replace it with 1.275 times xtrain divided by 255. Make sure I get the underscore in xtrain, minus 0.1. So what this is going to do is take xtrain and convert it to be a number between 0 and 1, which would be good. That would be pretty standard, but actually it's going to be a little bit better if we make the mean like a half or something like that. And so to do that, it's roughly, you would want the minimum to be minus 0.1 when it's completely black, and the maximum to be then 1.175 after you take away the 0.1, and then it will just work out with the MNIST data. And so we can also do the same for the test data to put it on the same scale. And this kind of pre-processing is going to like make things slightly more stable when we do the actual training. That's all, I think, for loading the data. So now we can move on to defining the model, which is going to be like a bit more intricate than previously we have had to deal with. But like I said, we can view this as a chance to kind of elevate our ability to write complex kind of nested architectures using just our sort of fundamental vanilla JAX components that we've kind of built up. And so let me start by defining actually this SimpleNet architecture, and we can sort of fill in the blanks. We're going to need some submodules. We can start with this and then fill in those blanks later. But let's start with sort of saying what is going to be in a SimpleNet all considered. So first of all, we got to actually register this as a pie tree in the pie tree registry. So we use jax.treeutil.register data class for that. And we have to also, of course, make sure it is a data class. So that will be data class wrapper to make sure that's the case. And then we have this SimpleNet. So we can define the components of the SimpleNet. And what they're called in the paper is we have one module called C1, which is going to be a 2D convolution. And then we have a module called S2, which is going to be subsample 2x2, which is a kind of pooling operation we would be familiar with in computer vision today. And then we have C3. So the numbers are indicating what sort of layer we're up to, and the letters are indicating what type of operation. So we have a convolution, which I've sort of simplified a little bit, and we have a subsample 2x2, so I've called it SimpleConv. This is going to be another SimpleConv 2D. And then we have, I think it's S4, so another subsample 2x2. And then one more convolution, but this is a bit of a funny convolution, I think, because it actually is going to have a shape of, it's going to have a shape that is more like a dense layer, but that's okay. And then we have layer 6 is going to be a fully connected layer or a dense layer, which we're going to call an AffineTransform. And then there's going to be a final layer is called, that we're going to call out, is the final output module, which is another AffineTransform. And so you can kind of, from this, imagine what the network is going to go. In fact, we're going to go through these layers in order. We just have to define what they are, and then we'll be defining how to like initialize them and how to put them together into a forward pass. But actually, I guess I'm going to write the forward pass now because, and we'll come back and write the initialization later, because this will give us a sense of exactly what is going to happen. And then when we're writing the other modules, we'll know where everything fits in. So let me go ahead and write forward now. And remember, we're going to do a single example, and we're going to use VMAP to batch this. So for now, what we need is just to take self, which is going to be a SimpleNet, so it's going to have these submodules as its fields. And then we're going to write the forward pass as follows. So we're going to take, oh, sorry, we also need an image input, but remember it's like a single image, so that should make things a little bit simpler. And so we know that the images in MNIST are 28 by 28, so this is going to be a 28 by 28 floating array. And then what is the output of our neural network? It should be some probabilities of each class. And so I'm going to say there's 10 possible classes because there's 10 possible digits, and so this is going to be a 10 floating array. Okay, so now we can write the actual forward pass. So first of all, we have to convert this image into an image with channels that is appropriate for a convolutional layer, the first convolutional layer. And so what that means is we have to take the sort of 28 by 28 image and make it instead a 1 by 28 by 28 image. And so, there are multiple ways of conventions for doing this, but the convention that I settled on for this code is to have the channel come first, although that is by no means the only way. And I think it's like not going to make a big difference at the end of the day whether this comes first or after the height and width or whatever, even if the height and width are in a different order. But we'll just make sure that we stick to this convention of channel, then height, then width. Okay, so once we've got that, we can actually pass through the first module. So we have self C1, which according to our conventions is eventually going to have a method called forward that is going to process the input and return some output. So we could do that. In fact, this is going to be a linear operation, and we could use nonlinearity. And Yann LeCun used a function called scaled tanh, which we're also going to define as the nonlinearity. So here I'm going to apply C1 and then apply the nonlinearity and make that the next value of x. Okay, and so then I can continue this with, actually, I guess I want to do basically exactly the same thing, but with instead of C1, I want to do S2. And this subsample module, we're also going to define that as having a forward pass, so that's fine. And then I want to do this with C3, and then I want to do it with S4. And so I've worked through so far my sort of modules, and there's a few more to go. And indeed, I'm just going to do those. So x equals C5. And by this point, I'm going to have a 120, but I'm going to be down to one channel, basically. So, sorry, not one channel, one height and one width. And so at this point, I want to flatten my my value so that I can put it into a dense layer. So basically, actually, let me annotate these with some shapes. So this will make things a little bit easier. So here we have 28 by 28 to 1 times 28 times 28. So one channel, and 28 is the size of our images. And then we're going to do C1, which is going to turn this into 6 by 28 by 28. And then we're going to do S2, and S2 is a 2 by 2 downsampling. So the job of this is going to be to keep the number of channels the same, but turn this into 14 times 14. And then we're going to do another convolution, which is going to also expand the number of channels, and this time it's going to expand it to 16. And I'm just getting these numbers from Yann LeCun's paper. And then we're going to have another downsampling, so it's going to take it to 7 by 7. And then we're going to have a final convolution, which is going to take it to 120 by, wait, no, sorry, I've forgotten padding. Yeah, that's right. So, what did I do wrong? So this one is not going to have padding, and so it's not going to preserve the 14 by 14. It's going to create a 10 by 10 because we're going to lose things from either side. Because we're not going to pad, and so the convolutions aren't going to slide all the way to the edge. And that means that by here, this is right, we're going to have 5 by 5. And then we're going to do C5 and create, also we'll have this padding issue. It's going to create a smaller thing, and we're going to have 120 by 1 by 1. So there's really only this like one location left in the convolutional sort of height and width space. And what this means is this layer is like effectively the output of like a fully connected layer. It's effectively flat. It's just these channels, these 120 channels. But we couldn't actually put this into an affine layer yet, like F6, because that's going to expect just a vector of size 120. So we need to do a ravel step. So jnp.ravel. So ravel, also called like flatten, is just going to take this and turn it into 120. Just get rid of the dimensions that are 1 and make it all 1 dimension. And then we're going to apply another layer. So now we're up to F6. So we'll apply F6 and we'll do another scaled tanh after it. So self.f6.forward of x, and it just so happens that this is going to take it to be an 84 dimensional vector. So this f6 is going to be from size 120 input neurons to 84 output neurons. And then finally, we'll apply the output transformation with no nonlinearity, because this is going to be our logits. And then we'll be ready to return. We could return x if we wanted to return logits. I'm going to return jax.nn.softmax of x so that I know the output is probabilities. And then we're going to write the loss function and the visualization functions to take that into account, that we'll already be getting probabilities out of our things in like linear space, not log space. Okay, so this is, oh yeah, I forgot to say that what this does is it already brings it down to size 10. So this output layer is going to be 84 to 10. And that is what we're going to do. Okay, so this is, we're going to implement some of the details of these submodules. And like we have to implement the simpleconv2d, the subsample, and the AffineTransform, as well as the scaled tanh nonlinearity. But you can see the overall picture here. And so now when we're implementing things, you'll see how they fit into the overall picture. I'll just pause here to note that in the original paper from Yann LeCun, there are a few differences to what we're doing here. So one of those differences is that instead of a linear output that is learned, like this will be, Yann LeCun used handmade radial basis function code that basically looked for, in the 120 pixels, looked for like shapes of actual numbers. And so it was just like hand designing one of the layers of the neural network in order to make it like learn a little bit easier and more efficiently. Let me see. I already noted that this layer here is basically a dense layer. No, I said this is basically like the input to a dense layer. It's worth noting that this convolution here is effectively like looking at all of the inputs and just producing one output of 120 based on everything in the image, because we're using a 5x5 convolution. So all of the data here is being seen in the one transformation. And this could have alternatively been a dense layer. We could have flattened at this point and thought of this as a 400 to 120 dense layer, and that would be equivalent. And then also to note that that in the original LeNet, the C3 transformation from 6 to 16 channels and down to 14 to 10 used some sparsity constraints that also were kind of informed by the problem setting. But we're just going to learn the whole thing, and it may end up being this 6 to 16 channels may end up having some like more dense connections than originally intended, or maybe it will learn similar sparsity by itself. I guess we'll just leave it to gradient descent to figure out what the best thing to do here. But Yann LeCun's original implementation had some extra constraints there. Yeah, so now we're ready to implement. We won't implement the initialization yet, but we'll just go ahead and fill in all of these submodules. And you're starting to see maybe how the modular approach is going to work. We're going to have a bunch of other classes like this that are going to follow this same API of having an init method and a forward method. And so without knowing the details of those modules, I can orchestrate them together in this forward pass, and then I can just implement the details sort of separately. But let's go ahead and implement those details. And I think for Python reasons, we're going to need to implement them beforehand so that when I define this class, these things are actually already available. And unless I'm using like a sufficiently new version of Python that this doesn't happen. But I think just to support older versions of Python, I should make sure we define these in the order that they're going to be sort of nested. And so that means I have to define SimpleNet last, because the data class itself sort of depends on all of these things. But I will go ahead now and implement them, AffineTransform being the first thing because it's sort of the simplest, and then we'll work our way up to we'll work our way through subsample 2 by 2 and then simpleconv2d. Actually, I guess the simplest thing to do would be to implement the scaled tanh, because that's just a function. So let me do that straight away. So let me just look up the constants that were used. The scaled tanh is just a tanh, a hyperbolic tangent, but with some extra constants found tuned by Yann LeCun to sort of work a little bit better. This is going to take basically an arbitrary array, and I'm not even going to bother annotating it because it's just an element-wise operation. This could be a scalar, this could be an array. Everything is just going to happen on everything in the array. So I'm just going to return straight away. And the weights that were used in the paper, 1.7159, and then that's the scaling of the jnp.tanh. So numpy has hyperbolic tangent, and so does jax numpy. And then 0.6667 times x. And so we basically downscale x a little bit and then put it through a hyperbolic tangent, which is like a classic sigmoidal shape. And then we upsample it again so that the eventual value is between, I guess, tanh is between -1 and 1. So this is going to be between -1.7159 and positive 1.7159. And that just turns out to work a little bit better according to the paper. I don't know. In today, we would sort of just use tanh, and I think it would like figure it out. But this is like a hyperparameter, I guess, that he must have found. Okay, so we're ready to implement the AffineTransform. This is going to be super simple. So we're just going to do weight, which is going to be our weight matrix. We've done this sort of before because we've done a multi-layer perceptron. This is going to be like half of our multi-layer perceptron, one of the transforms from one set of neurons to the next set of neurons with a weight matrix and a bias vector. And so this is going to be whatever. We'll keep the shape abstract so that we can apply it later. We'll have n in by n out as the shape of the matrix. I'll call this weights actually to match my solution and like I guess a little bit more common sense. And then we're going to have a biases vector, which is going to be array and size n out. So however many neurons we have on the output layer, on the output of this layer, we're going to need a bias for each of them. So we'll have a vector of biases. And then I can define my forward pass to take, again, self, which is a fine transformation, and to take a single input, which is going to be of shape, we can assume float array n in as the size, and then I want to have float array of n out as the output. Actually, I better make sure I have that. And then couldn't be simpler to actually implement this. We're going to take x, we're going to do a matrix multiplication times self.weights, and then we're going to add self.biases. We've done this sort of thing before. And then just to check the shapes, this will be n in vector times n in n out matrix, which will be n out vector, plus n out vector will be n out vector, and that's what we want. Okay, so cool. I guess we should also implement the initialization. So that will be, with our convention, is to make that a static method. And so we'll have def init, and this init better take a key, so a PRNG key array is the type annotation. And then we need to know the number of inputs and the num outputs so that we can define the right shapes. And then the output is going to be a AffineTransform. And so we're going to do something slightly different here than we have initialized these with random normal in the past, but we're going to initialize this one with random uniform. So let's return an AffineTransform. We'll do it all in one go here, basically. We're going to make the weights matrix equal to jax.random.uniform, and then we'll give it the whole key because we're not going to use a key for the biases. We'll just use those, make those 0. We'll make the shape equal to num inputs times num outputs, which is what we decided. And then we're going to specify, by default, I think this would give us between like 0 and 1 or something like that. But we actually want the bounds of the uniform here to be include negative numbers. And we'll make the min value equal to a bound that we're going to calculate, and the max value equal to the positive version of that bound. So the bound is going to be set to 1 over the square root of the number of inputs, which will just work a little bit nice. I can't remember if this was in the original paper or if this is like a modern thing. So in order to do this, there's like various ways you can do it, including 1 over like jnp.square root of num inputs. That's probably the simplest way to do this, and then we'll have that become the bound. Okay, so that is the initialization. Oh, I forgot the biases. So biases equals jnp.zeros. We don't need any randomness for this. We can just make num outputs zeros. Okay, that is the affine transform. So now parts of this code will work. The parts that involve the forward on the affine transforms will be defined. But we still need to do the other modules. So let's move on to the next one. And so the next one would be subsample 2x2, which is a bit of a weird quirk of this architecture, but for faithfulness, I guess this was not too hard to implement in JAX, so we're going to do it. Okay, so let's see. This one is going to be, well, we better just define the class to begin with. Class subsample 2x2. The components of the class are going to be again a weights, but it's not exactly a weights in the same way as we're used to. It's a little bit different, and it's going to be c by 1 by 1. And then we're also going to have a biases, but again, it's not going to be the same as an affine transformations biases. This is also going to be c by 1 by 1. The easiest way to sort of explain this is probably to just implement the forward pass and talk through it. So def forward is going to take obviously a self and a basically like a channeled image. We're on the way through the convolutional part of the network here. Remember, we're interleaving these conv nets or these conv layers, convolutional layers, and these subsampling layers, which, remember, when we're talking about the shapes, the job of the subsampling layer is to reduce the number of positions, like the height and the width, by a factor of 2 each. And so, so we can imagine that we have here a x, which is a floating array of channels by 2 times height by 2 times width, where height and width is like the eventual width that we're going to have, eventual height and width that we're going to have. And so I'm just going to annotate them as 2 height and 2 width, so that when I annotate the output, I can say that it's going to be a floating array of the same number of channels, but the height and the width will be halved to just h and w. And so in order to actually do that, basically, instead of when we would, these days we would use something simpler like average pooling, where we just take the average of the 4 pixels in each channel, or max pooling, where we just take the maximum of them. But here we're going to take a slightly different approach of having a learned, just taking the sum of the 4 values and then multiplying by a learned weight for that channel, and then adding a learned bias, which are the parameters here. So there's basically one of these for each channel. And so we'll do that now. And so in order to actually add everything in these like 2 by 2 little pixel groups, the easiest way that I found to do that is to use inops. And so I'm going to call the sums as inops.reduce, and inops reduce x from the shape CH2W2 to the shape CHW. And so this, oh yeah, we want to do the sum reduce, the reduce with the sum operation. And so this inops command is basically saying we're going to sort of talk about this height dimension as having h groups of 2, and this width dimension is having w groups of 2. And then in the next side, those 2's don't appear again. And so what that means is the reduction is going to happen within those groups. So all of the things within those groups are going to be replaced, are going to be combined into single entries using this sum operation. And so this is just one way to implement the grouping and summing part of this. But what we need to do now is take those sums and, like I said, scale them by the weight and add the bias. And so let's do that and return it. So we're going to return, and I've set this up so that it's sort of nice. With broadcasting, things will work out. We have a c by h by w array now. And so if I multiply it element-wise by a c by 1 by 1, the 1 is going to broadcast, and I'm going to get each channel multiplied by the weight for all heights and for all H and W indices. So for all indices along the height and width. And then I can do the same thing with adding the bias, and the broadcasting is going to happen again. So let's just do sums times self.weights plus self.biases. And there we go. So that's the subsample module. Oh, I guess I have to initialize too, actually, so I better not forget to do that. Static method def init. It doesn't take self, but it's going to return self. What's the input here? There's actually not going to be any randomness in the initialization, but we do need to know the num channel, so we can know what this C dimension is for our initialization of the weights and biases. And that's going to be an int, and the output here is going to be a self, and then let's get to it. So we'll return subsample 2 by 2, and we need to provide a weight and a bias. And the weights, because we are adding 4 things together, it makes sense to initialize the weights as 0.25, and that's what it says to do in the paper, I think. So jnp.ones of shape num channels 1 by 1. This will give us a bunch of 1s, and then if we just divide that by 4, we would get a bunch of 0.25s. And as for the biases, just like normal biases, we'll be initializing those to 0. So the effect of this at initialization, zeros num channels 1, 1, will be identical to if we were using average pooling. But it is then possible to learn the weight on the average and like a bias for the average. And those can be per channel. And for some reason, if you wanted to use this to affect the scale going into the next layer, the network could decide to do that with gradient descent. Okay, so let me see. So just taking stock, we've got our scaled tanh, our AffineTransform, our subsample 2 by 2. The only other thing that we mentioned in SimpleNet is the simple conv 2D. And this one is going to be the most involved of all of them, but it's still pretty simple. So we should be able to handle this. Basically, we don't have to implement the convolution ourselves because JAX provides that. We're just going to have to sort of plug it into some parameters and represent it as a data class. So let's go ahead and grab the sort of data class wrappers, and we're going to need to do something a little bit more complicated here, because the class simple conv2d is going to contain a field kernel, which is the convolutional kernel. That's a learnable parameter, no problem. The shape of this is also like a convention thing that you can kind of configure what you want, but I decided to go with kernel size by, because it's a square kernel, by C in by C out. And so this is the number of channels in and the number of channels out. So we saw before that this could be like 1 to 6 or 6 to 16 or something like that. But then also some of these kernels have padding and others don't. In particular, I think it's just this first one that has padding and the others don't. So looking at the shapes. So let's also have a padding parameter, which is going to be an int. But this padding parameter is not a learnable parameter. And so we have to make it that it's not a leaf of the pie tree. Otherwise, when it comes time to actually implement or do the grad transform, it's going to try and take derivatives with respect to this int, which is not defined. So instead of doing jax.tree_util register data class, we would actually have to transform this class by providing some commands, some arguments to this registration function. And so to do that, we're going to use functools .partial, which allows us to provide those at the stage of putting in the decorator. And then when we actually apply the decorator, it's going to apply a function of this with some arguments. And this is a very common pattern in JAX when we're using decorators. So data fields is the parameter we need for the things that are going to be leaves. And so kernel is going to be a data field. We just give it a list of the names of the fields that we want. And then we're going to call the next one a meta field. So meta fields is equal to padding. And so that is going to register padding as like part of the definition of the pie tree rather than as a leaf. And so that is part of the structure of the pie tree rather than a leaf. And so when we go to take gradients, we're not going to include the padding as a parameter. So that is something you have to sometimes do when you're registering your data classes, if your data classes contain kind of structural fields as well as data fields. If we had, for example, had the number of inputs be a part of the definition of the AffineTransform, then we'd want to do this similar thing there as well, because the number of inputs is not a learnable parameter. Okay, so now that with that definition of the sort of class out of the way, we can go ahead and implement the forward pass. And so the forward pass is going to be similar to others. We're going to have sort of self as the first argument here, and then we're going to have an input. And so this input is just a single input. I mean, remember, we're not worrying about batches because we're going to use VMAP. And so this is just going to be a channel in by height by width image data. And then the output is going to be a similar floating array of, there'll be C out is the number of channels out, and then the same height and width, or maybe a slightly different height and width, depending on exactly how things are padded. So we'll just use like an underscore to represent that this is a different version of that parameter. Or if you want, you could call this height in and height out. But I'm just using like height and as if this meant like height prime or something like that. And then the actual forward pass itself is going to be using the conv general dilated function from jax, which I have the documentation for. It's called jax.lax.conv general dilated, and it has a bunch of arguments, and you can read all about it here. It's very configurable. We're going to use just a subset of these arguments, thankfully. And so let me just write them out to show you what we actually are going to use. So first of all, we're going to need actually to, paradoxically, we're going to need to insert a batch dimension because jax lax conv general dilated is actually set up to use batches. And I found this a little bit disappointing because it sort of dampens the point of using VMAP. But what we're going to do is set it up to use a batch dimension of just 1, and then we're going to VMAP over it so that we don't have to worry about the batch dimension in the other parts of the network either. But this is set up to be able to handle in the back end one batch dimension. I'm not sure why. Maybe this is like slightly more efficient to do it this way or something like that. But I think once things are compiled, I would hope that it's actually equivalent. But anyway, we'll just need to reshape this x to, which is currently just chw to 1 chw. And so we could do this a number of ways, but I'm just going to use inops to make it really clear what is going on. We're going to take x, which is currently chw, and we're going to take it from chw to 1 chw. So that's just going to insert a free dimension at the start. Another way to do this would just do x and then subscript none or jnp.new axis. And then we'll do the same for we'll make the output of this transformation, we're going to call it y1 chw. And this is when we're going to call jax lax conv general dilated. Lax, by the way, is sort of a collection of backend functions. We already saw jax.lax.scan in the overture. This is another lax function. Typically it contains lower level sort of functions that are sort of more to do with details of calculations than the high level NumPy API. And convolutions are one of those things that is considered slightly lower level, so that's where it is. So to specify a convolution, you need to specify the right-hand side of the operator, which is going to be our x data, C1 chw, and then a right-hand side, which is going to be our kernel, which is our learnable parameter, and then window strides. We have to sort of say that we want to advance this kernel along the image one thing at a time, and then we have to say what padding we have, and I think we have to do this in a slightly weird format where we have to say something like how much padding on the left and the right and on the top and on the bottom, or on the top and the bottom and the left and the right, which would be like this. So we have self.padding self.padding for the height dimension. That's the below the image and above the image, or like I guess above and below depending on how you define it. And self.padding also for the better wrap this to make it nice and clean. Also for the width dimension. And then with that out of the way, we have to specify the dimension numbers. And this is where you sort of say, you can basically use any convention for the order of your various axes, as long as you tell JAX what you're using here. So if I say I'm using batch dimension, then channel dimension, then height dimension, then width dimension for the left-hand side. And for the kernel or the right-hand side, I'm using height dimension, then width dimension, then input dimension, then output dimension. And remember, that's because our kernel is height, width, C in, C out. So that's height, width, input, output. And then for the output, I want it to be batch, channel, height, width. So I'll say NCHW as well. So the same as the left-hand side. And so with these combinations of letters in any order, you can tell JAX lax.conv general dilated what type of how you want the axes to kind of correspond. And so you can have whatever convention you like as long as you do this. Now, before we return y, we have this extra batch dimension hanging around, so we have to get rid of that. So let's say ychw is just y1chw, and we index into that to get the first entry of the 1 entries in the batch dimension, and this will just be the chw part, and then we can return that. Okay, so that was a bit of a mouthful, but we have now successfully configured this convolution. And so the last step is to define one more static method, which is the initialization. Oh, I guess we still have to initialize also the SimpleNet itself, but that will come in a moment. Let's initialize this convolutional module. So for this one, we're going to need a few arguments. We're going to need, obviously, a key because we need to randomly initialize the kernel, so prng key array. And then also we should say what is the kernel size. I think this is always 5 by 5, so we could hard code this, but let's just keep it flexible for now. Num channels in is another integer, and then num channels out is another integer that we want, and then padding is another integer that we want. And so the return type of this is going to be self. And now how do we actually define this initialization? So we need to come up with all of the elements of a simple conv2D, so a kernel and a padding. Well, the padding is going to be easy. We can just return simple conv2D with padding set to padding, but we need to come up with this initial kernel. And for that, we need the rest of these arguments to decide the shape, and then we're going to need the key to decide the values. And so let's do a similar thing to last time, where we do the reciprocal square root of the number of inputs, and then use that to determine the values and use uniform initialization within that plus or minus that range. So we'll say the kernel is equal to jax.random.uniform, and we'll make the key equal to this key, which we're not using otherwise, and we'll make the shape equal to the shape that we need, that we sort of said we're going to have, is the kernel size times the kernel size times the number of input channels, num channels in, times the num channels out. And then that's going to be the kernel, the shape. And then we need the min val equals minus bound, and max val equals plus bound. And the max val is, the bound itself is going to be bound equals 1 over jnp.square root of the number of inputs. And the number of inputs is, let's count the all of the inputs in the kernel times the number of channels, because whenever we do this, we're looking at one location and then like 5 by 5 area around that, and then that's going to have some depth to it as well in the visual sort of in the image, where the depth represents like the red, green, blue, or like the 6 or the 16 channels or whatever that we're processing. So this is going to be num channels in times kernel size squared, and we'll take the square root of that and reciprocate it, and then that will be our bound. Okay, so that is finally done, and finally we're ready to go back to the SimpleNet and initialize all of these modules. So this is going to be a little bit tedious as well, but I'll just type through it because it's good to get practice. And this is also kind of important because this is going to demonstrate full circle. We started with defining forward in terms of these modules forwards, and now we're going to define the initialization in terms of the modules initializations. And so this is really showing our modular representation of, or modular way of programming neural networks. So it's worth it to see this in detail. So we're going to say that this is going to be another static method, init, which is going to take, we're going to need to take like all the parameters, but actually the network is going to define most of these parameters for us, and we actually are going to be able to hard code them. So the only thing we need is the key, prng key array, and then the output is going to be a SimpleNet. SimpleNet, okay, and so then we can just return SimpleNet. We'll just have to build it one thing at a time. And so to build a SimpleNet, we need to define all 7 of these components. And so I'm just going to copy this in order to save a little bit of typing. We're going to need to take this C1 is going to need to be a simple conv2d.init some things. S2 is going to be a subsample 2d init. C3 is going to be a simple conv2d init. Oh, I forgot init. Subsample 2x2 is again going to be subsample 2x2 init. C5 is another simple conv2d init. AffineTransform is going to be AffineTransform.init, and out is going to be AffineTransform.init. Now, some of these are going to require keys, and we need to split those keys up before we define any of them. And this is a good opportunity to show you another argument of jax.random.split, which allows you to split into more than 2. So by default it gives you 2, but if you just quite simply say jax.random.split key into 5, then you would get 5. So you can use this second optional argument to say how many pieces you want the split to have. And so we're going to need 5 because we're going to need 1 key for each of the modules that takes a key, and all of the modules except for the subsamples take random keys because they have learnable parameters that have random initialization. And so that was the convolutional layers because that's for the kernel, and the affine transforms for the weight matrix, but not the biases and not the parameters of the subsample 2x2s. Anyway, so the simple conv2d is going to have a key k1, and we'll use these just in order. Kernel size is going to be 5. We said the num channels in was going to be 1, and the num channels out was going to be 6. So num channels in equals 1, and num channels out equals 6. Subsample 2x2 just needs to know the number of channels, and so at this point we're operating with 6 channels. Simple conv2d init. Oh, I forgot padding, so I better make sure the padding is in there, and this one we said is going to have padding of 2. Now, simple conv2d is going to be the one that goes from 6 by 14 by 14 to 16 by 10 by 10. This is a 5 by 5 convolution without padding, and so we lose 2 from each edge, and so 4 in total. So we go down to 10 for the height and the width, and we're going from 6 to 16 channels. So this is going to be, we use K2, and then the kernel size is going to be 5 again, and then the num channels in is going to be 6, and the num channels out is going to be 16, and the padding is going to be 0 this time. Okay, subsample 2x2 for S4 is again just going to have num channels as the only argument, and num channels is now 16 because we just scaled up to 16 channels. Okay, the final convolution. So key is K3 we're up to. The kernel size is again 5. The num channels in is equal to 16, and the num channels out is 120. And the padding is again 0. And that means we're going to lose another 2 off either end, which is only going to leave us with actually the one thing in the middle. There's only one 5x5 convolution that fits in this 5x5 grid if you have no padding, and so, one kernel, I should say, that fits when we're doing the convolution. And so this is really just a 16 to 120. It's really just doing a dense mapping of size 400, and yeah, that's. But we're going to think of it as a convolution because that's what it is in the paper. Okay, and then F6. So F6 is going to use the fourth key, K4. We don't have as many inputs here. We just need to, because it's just a dense mapping, we need to know what the number of inputs is. The number of inputs is just the 120 that we have coming out of here. Remember, we do a ravel in between to make sure that this has the right shape. But that's all handled by the forward pass. And the num outputs, we wanted it to be 84 outputs. Okay, and then the final transformation is going to be K5, I should say. Num inputs is going to be 84, and we need 10 outputs to represent our logits. So there we go. So that is the initialization. It just fits on my screen, and we have now finished implementing the architecture section. So we had the various modules and the scaled tanh function all represented there. And now we can finally come back to the main function and actually initialize the model. And the code here is going to be so simple because we've got everything handled below. But we need to do it. We need to have key model init split off from our key is jax.random.split key. And then I guess, what should we call it? Just make sure I follow my prepared thing. I guess we're just going to call it model. That's very uncreative. Model equals SimpLeNet .init, which, remember, just takes a key model init. And so I think we better run our code at the moment to make sure nothing is going to go wrong. Oh, okay, so this is one thing that's going wrong. Again, this is the Python issue. So I'm going to need to actually take all of my architecture section and move it before the main function and the training loop. So I've just done that in code folding mode. So now I've got the architecture, and if I scroll all the way through this, we'll get back to the code. Still going, still initializing. Now the training loop. Okay, so you're going to want to do that in your editor as well, and I'll apologize for that. And now the SimpLeNet should be defined by the time we... wait a second, the SimpLeNet should already have been defined. Scratch that. Okay, we can put the architecture back. The problem here was actually coming from me. This is, if I look at the actual line that this is defined on, I needed to return self here. This should be self. That is the problem. So that will go away in a future version of Python. Okay, so yeah, there's another typo. Instead of biases, I wrote biased in subsample 2x2. So hopefully you didn't make that typo yourself. You might have some other typos, fix them up. We did a lot of typing, but this seems to be running now. And if I go back to code folding and go back here to my part of the main loop where I defined the model, I've got it. It would be nice though if we could somehow like print out the model to sort of see what we've done. And to do that, I think we should use, we can do that. If we print out the model itself, we're going to get all of these weight matrices, which is going to be huge. There's a lot of parameters in this model. So let's do something different instead. Let's print jax.tree.map lambda leaf jnp.array of l.shape. And let's map that over the model. So let's see. Actually, I don't know if I need this jnp.array. I can just take leaf.shape. Let me call it leaf2. So leaf. So what this is going to do is this jax.tree.map is going to walk over the SimpleNet pie tree, which, remember, we've registered all of these data classes as pie trees, which means all of their fields are like the children in a tree shape. And it's going to, for each leaf, which means every learnable parameter, so everything except for the padding of the simple conv2D modules. And this is going to represent, this is going to walk over them and apply them all to this function. Apply this function to all of them. And so they will become input, and the output will be a shape, which will just be a tuple of integers. And then it's going to return a pie tree that has the same structure, but with the outputs of this function. And so this is going to be a pie tree that has the shapes of all of the submodules. And so now I can print this because this will fit on my screen, and it would just replace all of the arrays with their shapes. And so you can see this here. It's a SimpleNet. It has a C1 field, which is a simple conv2D, which has a kernel, which is a 5 by 5 by 1 by 6 matrix. It also has a padding of 2. I guess it prints that out too, but it didn't apply the map to it. And then we have S2, which is a subsample 2 by 2, which has a 6 by 1 by 1 weight and 6 by 1 by 1 bias. And then we have C3, which is a simple, and you can see this is going on. We have S4 here, and we have C5, and then F6, and then eventually out. And so all of the components are there. And if we wanted, we could actually just take maybe jnp.prod of leaf shape, and it would tell us how many parameters there are, or not. Yeah, okay, so tuple. So actually this is not going to work for tuples, but I can do jnp.array of the leaf shape, and then that would work, I think. So we convert the tuples to integer arrays and then take the prod, which is going to multiply them. And now I see I have biases array 84. So there's 84 parameters in this bias of this F6 AffineTransform, which makes sense because there was 84 output neurons. So just to pick a random parameter. And then what's the easiest way to sum along this? I guess maybe if I was to say jax.tree.leaves of this, I think that would give me this as a big list, and then I could just sum over it. It's getting a little bit messy. I'll write it out again in a moment in sort of like neater format, but this should give me the total number of parameters in the model. And we've got 61,608. That sounds, I guess, about right. I haven't done this before, actually. Let me do this a slightly easier way, actually. So keep the sum, make this a list comprehension of, prod jnp.prod of jnp.array. Oh, actually, I guess I can just do leaf.size, right? I don't need to take the shape and then the prod of that. I can just do leaf.size. Size always counts the parameters. For leaf in jax.tree.leaves of model. So now look at this code. Ignore this behemoth that I put below. We've now got a list comprehension, just plain Python, that is going through an iterator, which is taking all of the leaves of the model, which is a pie tree. And for each of those leaves, we're taking the leaf, which is a matrix, and we're computing the size. And then I'm summing up that the entries of that list, and that should give me the number of parameters. And so there we go. So that's a slightly simpler thing than what I worked up before. But, both of these showed you various pie tree operations. Okay, when are we going to VMap? We're nearly there. We're ready, basically, to VMap, because we're ready to start training. We're going to need some batches. So we'll do VMapping in a moment. So let's get started with the training. Oh, you know what? Maybe we should just test a forward pass first, actually. A single forward pass, and then I promise we'll VMap. So let's say, what if we put this image through the model? So we should be able to say, instead of mp.image xtrain 0, let's do, we will print it. We'll do print model.forward of xtrain 0. I hope this works. So here we have the number of parameters counted and printed again. And then we go through the model, we put this image through. This is the 5, remember, and it's telling us that it has like a roughly 10% probability to be any of these images, which is sort of fair enough if it hasn't seen any images before, that the first time it sees these images and we ask it which one it is, it should predict sort of a uniform distribution over them. So that's pretty sensible. Not quite uniform because it was randomly initialized. Okay, so now that we've tested that works, we can finally get to the training loop. So for this one, I'm going to need to define some lists first, so we can do our plotting. I'm going to need to keep a history of the losses and the accuracies from every step. And then I'm going to go for step in range num steps. And we're going to do a simple sort of thing like we've done before. We're basically going to sample a mini batch, which we're now calling a batch following just standard conventions. We're going to compute batch loss and grads. We're going to apply the grads to our model using tree map. And then we're going to track some metrics, and then we're going to do some visualization. Yes, let us sample a batch. So we're going to need a key for this. I'm going to break my rule from last time of defining a specific key for the training loop and then forking that key, and just show you that you don't have to do that. We're not doing anything afterwards with the key, so this should be fine. So every time around the loop, we'll just fork a new thing off our main top-level key for the main function. And then the batch IDs is going to be jax random choice. This is very similar to last time. We're going to choose a random batch of MNIST digits with this batch key. The number of examples, y train size, this will tell us how many things. We know there's 60,000, but this will just give it in code. Shape equals batch size, which is really our mini batch size. Remembering to do it as a tuple this time because I think it didn't work last time. And then replace equals false to make sure we don't get any duplicates in the one batch. Yeah, it would normally be the way we'd do it is we would have epochs. In each epoch, we'd shuffle the data set, and then we'd we'd sort of chunk it and load them one at a time. Load like one mini batch at a time. I'm just doing this because it's a little bit simpler to code up in sort of to live code up this way of doing things. We're going to use these batch IDs to take xtrain and take the batch IDX and get the elements for today's batch, and then y batch equals y train to get the labels. I guess one reason why you might do it the sort of shuffling way is that it gives you everything fits in memory for this small data set, so it's not an issue, but it gives you better locality of sort of working. You shuffle things and then you work through them in one go, and you're sort of always loading the necessary part into memory or in the cache or whatever. Whereas this is going to be going all over memory for a general data set, this method. Anyway, so now we are ready to compute the batch loss and grads. This is like we wanted. We need to define the loss function, I suppose, which is going to need to do some vmapping. So we're really getting close now. So let's say loss and grads equals jax.value and grad of what we'll call batch cross entropy applied to, let's say we're going to pass it the model, the x batch, and the y batch. So the inputs and the outputs that we expect. We'll define that batch cross entropy in a moment. Actually, I guess we'd better define it now because this will force us to do the actual vmapping, and then we can come back and update the model and track the metrics and do the visualization afterwards. Okay, so ready to define some metrics and do some vmapping. So we're going to need to define cross entropy, and we've done this before, but let's do it slightly differently this time. Because we have outputs of our model are now probabilities rather than logits, the formula is actually going to be slightly different. It's also easier to sort of understand. Let me just flick down to it in my code so that I can make sure I'm not making any mistakes. So cross entropy, we're going to take a model, which is going to be one of our SimpLeNets. We said we'd take our X is going to be a batch of X is going to be a batch of examples, but this is cross entropy, not batch cross entropy. So we can just handle a single one here. So this is a float array of size height by width. It's just a single MNIST digit. In fact, this is 28 by 28, but that's not going to matter. We're going to have y as our single integer, or uint8 actually, representing the label. And the output should just be a single float. So this is just going to be a very simple function to think about. And the formula for the cross entropy given, some probabilities, is going to be we're going to take model.forward and x. That's going to give us the probs. Let me spell this out. Probs. And then the probability of the correct class is going to be probs y, because y is an integer. We can just index into this array, which looks kind of like this. And then we're going to index in, for example, for this one, 5, we'd go 0, 1, 2, 3, 4, 5. You know what? I actually think that it just so happens that 0.1056 is the highest among all of these, which means this is actually the correct answer, is the most likely one that this randomly initialized net has made, which is pretty cool, but it's obviously just a fluke. Anyway, so this is the probability of the true class, and we're going to take the negative log of that, and that is going to be the cross entropy. Because remember that cross entropy is defined as the sum of the probabilities weighted by the true distribution, or like the expected value under the true distribution of the log of the probabilities, negated then to make it an entropy. And so here we have this sum actually reducing to just indexing because the true distribution is concentrated all on this one output. So we're basically querying this probability, computing the log, and then summing all of the rest of the terms in the sum defined to be 0, and we're giving that negative as our output. So that's quite a simple function to sort of convert from mathematics to code, because we didn't have to worry about any batch dimensions, but we do eventually have to worry about batch dimensions so that we can actually get this in our code. We need to run the batch version of this. So we need to do some vmapping now. So batch cross entropy. And so batch cross entropy is going to take model SimpleNet x's, which is going to be our float array with batch size, and then height, and then width. And then y's is going to be our int array. Yeah, that's right, int array batch size. Actually, I guess technically it's a uint8 array, but this is just a type annotation. I think it's good enough. And we still want to float a single float out, actually, because we want to take an average over the batch. And so now we need to use vmap. So vmap, jax.vmap is going to be able to give us a version of cross entropy that is vectorized. And so jax.vmap of cross entropy will give us a version that takes batches of everything. But we don't just want a version that takes batches of everything. Let me call this vmapped cross entropy, or vectorized cross entropy. We'll call it vmapped cross entropy. Cross entropy, we don't want it to take vectorized models, for example. We want to use the one model, and we want to vectorize over just the x's and the y's. And so we need to say in axes equals no in axis for the first argument model of cross entropy, and then make a dimension at axis 0 for the other two positional arguments. And that is what we want to do. The out axis is fine to leave as the default as just 0. So that instead of a float, we're going to get an array back. And so now we'll say all cross entropies is this vmapped cross entropy function applied to our model and our batch x's and our batch of labels y's. So this is now going to give us, oops, I've got a typo. This is now going to give us a vector of cross entropies, a vector of floats of size batch size, because that was our batch dimension on the inputs. And so this, another way to say that is this going to be is float array batch size. And so in order to turn that into a single float, we just need to take the mean. So we'll just return jnp.mean of all cross entropies. And there we go. That's our first use of VMAP. And so this has saved us a bit. Basically, what we could have done is we could have defined these probabilities for a batched forward pass, and then we could have returned the negative log probabilities. We could have done some weird batch indexing here. Would have been a bit of a headache to get just the probabilities from the respective class labels. It's a bit of a pain to do that kind of indexing in NumPy and in JAX. But in doing it this way, we didn't have to do it. We just transformed our function and said what inputs we wanted to be batched, what inputs we wanted to keep the same and broadcast over all of the other inputs, and we got our output, and then we would just take the mean to convert that into a single output. Okay, so we can continue now. There's more to do, but we can continue with our training now. And so so now it's time to apply the gradients. Now this should be defined. And so this is going to be the same as last time. So we're going to take a new model. Is going to be equal to jax.tree.map of a sort of update function, lambda, I'm going to call this w and g instead of like leaf w and leaf g or whatever, because I'm not using these parameters now for anything else. And this is going to be w minus learning rate times g, which is the standard gradient descent rule. And then we need to say what we're mapping over. So we're mapping over the model and the grads, which is going to be a pie tree just like the model. By the way, I think it's pretty cool that like this value and grad transformation basically we give it an arbitrary pie tree, which is going to be a SimpleNet. It's going to give us a SimpleNet of gradients out, and then we can just do this mapping over both of those at once. It's pretty cool. It's all with our custom defined model that we just spent so long typing out. Okay, anyway, back to actually coding. I'm just going to see what we have to do to track the metrics. So losses.append. Losses is our list that we defined at the start of losses. So we're going to append this loss to that. And then we should probably also compute accuracy every now and then, and accuracy on the test set. And I don't want to do the whole test set because that would actually be like pretty big. It's 10,000 images all at once. But we can easily just do like the first 1,000 of the test examples, and that will give us an estimate of the full test accuracy. So test acc is equal to, we're going to have to write this function batch accuracy, but we'll do that in a second. It'll be another chance to practice vmapping things. Xtest, we'll give it the first 1,000 things, actually like this, from 0 to 999 of xtest, and then we'll do the same for ytest. I guess we should, technically, if we were developing this, hold out a development set to do our evaluation on while we're developing, and then use the test set only later for like evaluating the actual model that we want to publish. But we're just, no one's training on MNIST anymore. It's overfit to hell, so we should be able to get away with this. And then we want to append the accuracy to our accuracies. Actually, for some reason, my data here is of the format step loss, and it's because I'm going to be doing a scatter plot later. So I'm going to replace this with tuples in this list. So this is actually going to be a list of pairs of integers and corresponding scores. And so this would also support if you wanted to only take this test accuracy. If you only wanted to evaluate every few steps, you could still be able to get an accurate scatter plot because you're logging when you took the step for the time series. Okay, finally, visualization. And so in the code, there's this steps per visualization, but I'm going to get rid of that because I don't think it's necessary. It'll give us a slightly more dynamic visualization if we get rid of it. And I want to say we're going to create some plots and then print them out. And so let's create a plot of the classification of the digits with its visDigits function, and then a plot of these metrics with visMetrics. So the digit plot is going to be this function we prepared earlier. So visDigits, I'm going to give it some test digits. I want to test on some specific digits that I think do interesting things. And those are the digits 1, 6, 7, 8 from the test set. And so I'll do those as the digits. And we need to specify the labels. and that's going to be y test. That's going to be y test 1, 6, 7, 8 as well. And then I have to specify the model. Oh, you know, I haven't done the batch accuracy. I better remember to do that. And we'll need to do that before we see anything. But I'm here now, so why don't I just continue writing this visualization code, and then we'll come back to it. So we then want to do a metrics plot, and that is going to use vis metrics. And that's going to take our losses, our accuracies, which are these growing lists. And so every time, every step, we're going to give like a slightly expanded list, and then this function is going to plot it as a scatter plot so we can see the curves growing. Need to say what the total num steps is, which is just num steps. It was one of our configuration parameters. And then I don't think we need to say the current step because we just need this to know how big to draw the axes and like how much progressive training we've made with the data points in these lists. So we've got two plots here, and we can basically print them out. But before printing them out, I'm going to combine them. And so I'm going to make a single plot that I can print all at once, because then I can also scrub it all at once with the negative plot trick. And to do this in matthewplotlib, you just have to say, I want digit plot over metrics plot. And then you've got a new plot that is like the digits plot and then the metrics plot underneath it as sort of two subplots. And then we can print. We haven't printed out this plot before, actually, so before the training loop started. So I better, because it takes a little bit of effort, obviously, to set up. So I better make sure that if step is 0, then I print the plot just plain, and otherwise, then I want to scrub it. So print, do this trick of negative plot followed by plot, and that should basically work. So yeah, this won't work yet because we need our accuracies. So let me just define the accuracies, and then we will be ready almost. Actually, I think I need to define one more thing maybe after the accuracies. But they both use vmap, so that's what we're here for. But anyway, we're ready to implement. I like to have 2 spaces between my things so that my code folding works properly. Let's define the batch accuracies. So batch accuracy, actually I think we don't need vmap for this because accuracy for a single example is just whether or not it's correct. And so I actually think this is a case where you can get away without vmap. But we could do it. You could do it with vmap if you like. It might be an interesting exercise to try and do this with vmap and see how different it would be. I think it would be a little bit too trivial. So sorry about the broken promise that we were going to use vmap again here, but we will get to use it one more time before the end of the lecture in a moment too, because some of the visualization code relies on having a batched forward pass, and I need to write that. So we're going to have x's, which is our float array of batch size, height, width, and then y's, which is our float or int array of batch size, just batch size. And then the batch accuracy should be returning a single float. Okay, so yeah, we will need, actually for this, we will need to do vmap because we need to vmap the model forward pass. And so, so basically, because I want to get the probabilities for all of these examples all together. And previously, you can see what we did is we did the model forward pass inside the cross entropy function. And then when we did the batch cross entropy function, we vmapped the whole cross entropy function, which includes adding a batch dimension through the model. And so this is actually an interesting point about vmap, is that you only have to vmap at the outer layer, and then the vmap will transform all of the functions that function calls, and also add the batch dimension through them if it's relevant. And in this case, it's relevant because X was one of the things we vmapped. But also, interestingly, we could have vmapped models, and then this would also vmap forward in like the other direction. And so, yeah, that's pretty interesting, is that vmap you only sort of need to do it once. But in this case, it's natural to, we still need to process the batch, but we're going to need to, we don't have this cross entropy function that we're going to vmap that calls forward inside it, so we just need to vmap the forward pass itself. And it's actually quite common to vmap the forward pass of the model. And so what I'm going to do is I'm going to go back in my code folding to the architecture and where we defined the model itself. Actually, it's right here above in the forward pass. And I'm going to add another method that is called batch forward. And this is going to become standard in my neural network, sort of my convention of programming neural networks, is I'm going to define forward and then I'm going to define batch forward. And so I'm not going to define it for all of the sub-elements of this architecture because, like I just said, we can just do the top-level vmap here, and then it can cover all of those as well. But I'm going to make a version of the method for anyone who wants to call my neural network, my SimpleNet, with a batch dimension. So this should be batch size 10. And then you can give the single model and a batch of images, a batch of inputs, 28 by 28, and a floating point batch of outputs of size 10, vectors of size 10 you will get as the predicted probabilities. I'm going to do the vmap inside here. So I'm going to say vmapped forward equals self.forward. Vmap, jax.vmap of self.forward. Now, pay attention closely here because self.forward is a 2-argument function, it would seem. Self and image. And so you might think that we need to provide in-args to say that we only want to forward pass, we only want to vmap the image and not the self. But self.forward is actually not the same as SimpleNet.forward, which is the 2-argument version of the function, which sometimes it's useful to have. If you do want to vmap over self, you would want SimpleNet.forward. But here we've got self.forward, which already has self, it's already partially applied to self. And so this is actually only a 1-argument function, which, when you normally call this, you would recognize that you just provide 1 argument, the image. You don't provide a second argument of the self as well. It's already provided here. And so when we vmap this function, we actually don't need to worry about providing in-axes because by default, we're going to be vmapping over an extra 0th dimension of anything. So it's going to work exactly as we intend with no extra arguments here. Anyway, so then in that case, I just need to call vmapped forward on my images, and that will call self.forward with all of the images and return a array batch size 10, 1 float array 10 for each of the things in the batch, which is exactly what I want to return. So that is as simple as that. And now this batch forward function, anytime that I want to use this neural network in sort of batch mode, I can call it. And so I'm going to do that in batch accuracy as an example. I'm going to say the pred prob all classes is equal to model dot batch forward of x's. Make sure I type forward correctly. And then in order to calculate the accuracy, so that's that. And I'm also going to call this function somewhere in the visualization, I think. So batch forward, batch forward comes up again in viz digits, and that's all. So it's getting some extra use as well, but I only vmapped it sort of once. Actually, I guess it's vmapping every time you call it because it's vmapping it inside the batch forward method. But when we do just-in-time compilation later, that's going to make sure that it only actually happens once. Okay, so predicting the probability for all classes, model batch forward. We've got the predicted probs for all classes. So this is our batch size by 10 array. And I want to figure out what class do I predict for each of those. And to do that, I need to look in this array. In each row of 10, I need to figure out what is the index of the maximum prediction out of those. And so argmax is the appropriate NumPy method to do that. And so I'm going to say the highest prob class, I'm going to try and type, prob class is equal to pred probs all, or pred prob all classes dot argmax axis equals 1. And so it's going to go along the the 0th axis is the batch dimension. I'm going to be going along the first axis, the axis index 1, and getting the argmax there, which is going to be the highest, the index of the highest entry in that row. And this will return to me a batch size vector of indices of those. And so I can compare that directly to my y's, and I can say a vector of whether I was correct or not, we can call like correct classifications, is just going to be y's equal to highest prob class. Just put some brackets here so this is a little bit more readable. And then this is going to be a vector of booleans, and it's going to be true whenever the highest probability class was equal to the label, or the index of the highest probability in the vector of 10 is equal to the label. So for example, in the first case, because the index 5 position was the highest, and 5 is also the label, this is going to be a match and this is going to be true, whereas for others it's going to be false. And so if I want to calculate the proportion of these that are true, then one way to do that efficiently, or like at least succinctly, for a NumPy or JAX array is to use mean. So return jnp.mean of correct classifications. And this will basically treat all of the trues as 1 and the falses as 0, and it will calculate the sum over the total, and so that will be the number of trues over the total number, and so that will be the ratio of true, which is also the accuracy as a floating point, which we can then read as a percentage. That's batch accuracy. And now I actually think we're finally ready to run this code. So there might be some bugs, but we're going to flick back up to the training loop and just confirm that what we were up to here. So we've figured out this batch accuracy. That's now implemented. The other thing I was worried about was the batch model, and that's required for some of the visualization code. I think if we run this, okay, I've got some typos. What line is this on? 324. Cross entropy has to have a paren there instead of a square bracket. Might be some more issues. Counting the parameters, no syntax errors. Now we're training. Please work. Yes. Hey, it's working. So what you can see here is the visualization of training. So we're training, and we're going to show the p-digit given image. Why can't I highlight? Okay, I'll figure that out later. There we go. It's because it's printing. Okay, so p-digit given image. This is a sort of column chart representing what the network thinks, the probability distribution coming out of the network for this image. And you can see it's very likely to be 2. And so I've colored this one in green. Whereas over here, it thinks this is a 6, whereas I think the official classification is it's a 5, and it looks a bit like a 6 maybe. And this one it also gets right as 4, and this one it thinks is 9, but it's sort of closely followed by 4. I guess maybe it looks a little bit like a 4, depending on how you look at it. Oh, by the way, I've downsampled these images. Of course, the full images are 28 by 28, but to make them fit, these are now, I think, 7 by 7, so they're just a quarter of the size. And we also see these loss curves, and you can see that, as the training steps progress, the cross entropy goes down and the test accuracy goes up, and we end up with 90.6 as our eventual loss. So that's not bad. Yeah, let's run it again and watch it again. We'll just watch it again, and then we'll wrap up. So it takes a while. Once we JIT this, things are going to be running quite a bit faster, but for now, we are seeing it is able to run and just slowly print. And I didn't do any sleeping, by the way, in this case. Notice there's no actual use of time. Maybe I can get rid of the import, in fact. And I don't need to because it's doing it's doing enough computation to sort of make this take time. Computation and printing. You can see like a little bit of a flicker sometimes. As it sort of struggles to keep up with the printing. Yeah, actually, it's going pretty slow right now. I wonder if maybe something is a bit slow with my computer. Yeah, this is working. I'm not sure why it's slowing down so much. This was running faster before. Yeah, it could be that this. Yeah, I'm seeing a recording overload, so I'm gonna quit this. We already saw it finish. Yeah, I think this might be just eating up some of my too much of my RAM while I'm also recording. But that's okay because we already saw it complete and it's working. And one thing that I did in the code, you know what, I'm going to make this run a little bit faster. So I'm going to do the thing that I said I wasn't going to do. And then we can wrap up. So I'm going to add back num steps per visualization, I think it was called. Let me just double check that to make it consistent. Just steps per visualization. And so to reduce the amount of time that I'm spending doing matthewplotlib stuff, rendering and printing this plot, I'm only going to print every few steps. Let's make it that we'll only print every 4 steps by default, and we can change that as a parameter. And then in this printing logic, this visualization logic, I'm going to say if steps mod steps per visualization equals 0, or in the special case where I want the last step, so we always get the last step, steps equals num steps minus 1, then I want to do this rendering and printing. And in fact, I might put the test accuracy, this is also, we're going to evaluate every few steps, and we're going to visualize every few steps, but not every step. And so this should reduce the amount of computation that we're doing and maybe make this run a little faster. But you'll see it being a little bit more sort of incremental, unless I've made any typos. Okay, so it should be not steps equals, but step equals. And then also here, no, this is, step. So steps per visualization. So this is every 4 steps, this is going to be true, and this will be true for the last step, even if it's not a multiple of 4. We can now wait for this to all load, and you can see there's fewer points here in the test accuracy curve because it's just doing every 4, so it's subsampling those. There's just as many in the cross entropy, and this is flicking every sort of half a second or so. Okay. So we'll let this run to completion and then wrap up the tutorial. So I want to leave you with a challenge. This is a very long one, so thanks for sticking through. I hope you learned a little bit about what it's like to build bigger neural networks with JAX. And this is just vanilla JAX. There's also like frameworks you can use to help compose even larger networks, but it is possible to sort of do it by hand, and that's what we've seen today. And then what we're going to do is we're going to keep building similar things like that in the future lectures, and we're actually going to spend some time optimizing this training code, this one, using a better optimizer and then JIT in Act 2. So we'll be spending a little bit of time with this code base, and it will have been worth the investment today. And you might also like to explore it yourself, and I'll leave you with the challenge of training an ensemble of convnets, an ensemble of SimpleNets. Get an army of SimpleNets together and then pool their predictions and take the average prediction and see if you can do better than the 90%. I think it should be quite easy to do better with this 90% than by like training longer, for example, or using a better optimizer or so on. We're going to explore some of that in future. But for now, try an ensemble. So this is another chance basically to use VMAP, by the way. So when you predict with an ensemble, you need to do the forward pass of multiple models on the same data. And so that's another chance to use VMAP. You can VMAP over the entire model argument as well. And so you're going to need to use the 2-argument version of the forward pass to do that. But you can train all of the ensembles. You can VMAP the training step. You can use VMAP wherever you see fit to make this happen. And I think this is a bit more challenging than some of the previous challenges, but I think it will be worth trying to do, and it will be a worthy challenge. And so I'll see you in the next lecture.